Hello, in this video we're going to look at another simple machine, this time the wheel and axle. I've done a quick mock-up of one here. So we've got the big wheel with a handle on it. We're rotating this handle in some direction, so let's say clockwise direction there. That is going to turn this axle in the same direction. So we're not getting a change in direction of our motion here and change in direction of the force. We're just getting the change in magnitude on that. And that change is going to be, as usual with simple machines, based on the geometry of the setup. So if the diameter of the wheel is capital D and the diameter of the axle is small d, then the mechanical advantage in the idealized case, which of course is equal to the velocity ratio in the idealized case, is going to be capital D divided by little d. Now, how is this of any use? Just putting on there, that's 100% efficiency. I mean, things will change when it's not 100% efficient. How is this of any use? Well, quite often we'll say we'll be wrapping a rope around here, which would be then hanging down. We're going to have some load. So this is going to be our load. This is going to be our effort that we're applying. You get various intricacies of the different ways wheels and axles could be set up. So if you were thinking of this as being a horizontal setup where, I don't know, we're taking a bucket out of a well, say. I think the technical name for that is a windlass. But that's very similar if we turned it on its side, and you often see these on big boats where you'll get these horizontal wheels with these multiple handles coming out the side, and you'll see sailors as a group going on these and rotating them all round. So we've now got a vertical axis of rotation rather than the horizontal one that we had for the windlass. These are called capstans, assuming I've spelt that right. But yeah, I think that's how they're spelt. So they're capstans. They're more or less the same thing. You would have also come across winches. Must admit, I'm not entirely sure exactly what the technical difference between all of these are. I think winches, I mean, you get a lot of those on boats as well, don't you? I think that's more for wrapping up the cables. But if you want to go all nautical and look all of those up, then yeah, go for it. They don't necessarily affect things here in terms of our analysis. So if we were going to analyze one of these wheels and axles, which we know we can do fairly simply, it's the same thing. We can measure these distances using a ruler. We can measure our effort with a force meter. We can measure our load with some scales. So these are all very measurable things. So say our capital D was 12 centimeters, our little d was 2 centimeters. Then we can see straight away off of that we got a velocity ratio of 6, the 12 divided by the 2. If we saw that, say, let's stick with these numbers, that 12 newtons lifts 60 newtons, then we can see that our mechanical advantage is equal to 5. So that immediately gives us the efficiency. So once again, efficiency is very easy to work out on simple machines because that's going to be mechanical advantage divided by velocity ratio. So we're around 83%, give or take, on efficiency. It also allows us to work out our losses because, well, how much of our 12 Newton effort that we've put in has been lost here? If we wanted to lift 60 Newtons and our machine was 100% efficient, then we should be getting, well, 10 Newtons would lift 60 Newtons if 100% efficient. But we're having to use 12 Newtons. So we've got that difference there of this extra 2 Newtons that we're having to put in order to lift the 60. So we're doing 2 Newtons of work against friction. And we're just losing that in our multiplication. So our ideal mechanical advantage is multiplying the 10 up to the 60. And that extra 2 is just lost. So quite simple calculations again. you'll see the similarity between the wheel and axle and screw as well. I mean, one thing I suppose with the screw is quite often you're looking at the distance that we're rotating. I mean, you could do that on this as well. You could look at the 2 pi's are cancelling in wheel and axle. If you're going to do a 2 pi r of how far have you actually moved your handle through, well, you'd have a 2 pi times big R and a 2 pi over little r, and we're going to get the same d over d thing that we had before. But there's a lot of similarities here between wheel and axle and screw, but we don't have that change in direction of motion. Yeah, so there you go. It's a quick summary of what's going on with wheels and axles. They're quite a simple one. I mean, these link in, actually, before I forget, to cog systems. This is another thing where you can start changing the direction more. And we'll look at some of these in compound machines. But when you bring in gear systems, then you can translate force around. If you had you turn a wheel, so we've got our wheel again. We've got an axle which might have then a cog on the end of it. You can then mesh that cog with other cogs. Terrible drawing, but you get the idea. So we've got a few of these cogs. As you turn that one that way, it's going to turn that cog in the opposite direction. Depending on the number of teeth in each cog, you're going to get different amounts of or different rates of rotation. So the bigger cog, it's obviously going to take longer to rotate than the smaller cog. So this is where you get all these things with gear ratios, where you're looking at ratios of the number of teeth in these cogs as they interlink with each other, and that's giving you then changes in our velocity ratio and such like. So we'll be able to look at the motion of the big wheel on the way in, so say your pedal on the bike, and then how that is going to relate to the gear that you're actually using on your wheels. But I'll do separate videos because, again, this is getting into compound machine territory and more complicated machines. So I'll bring that into a later video of how we're looking at gear systems.